concepts of thermodynamics. The screen is visible to all of you. Students, is it visible?
Yes,
Screen is
sir.
visible?
Yes,
Okay.
sir.
Uh, so you remember, just I'll revise the whatever the applications of engineering thermodynamic systems are: steam and nuclear power plants. Internal combustion engine means the combustion of fuel takes place inside the engine cylinder. In internal combustion engine, chemical energy of fuel is converted into the heat energy. That heat energy is used to run the vehicles. Gas turbine turbines are the power generating device where uh, we'll get the power. Okay, and gas turbines means working fluid is gas. Like that we are having the hydraulic turbines and the steam turbines. In hydraulic turbines, we studied in sources of energy in hydraulic power plant. Okay, so the working fluid is water. The potential energy of water is converted into kinetic energy of water, and then kinetic energy to mechanical energy by means of rotation of shaft, and then uh, mechanical to electrical by means of generator. Air conditioning, refrigeration, gas dynamics, jet propulsion, compressor, chemical process plants, and all the direct energy conversion device are the practical applications of engineering thermodynamic systems. Okay, and we studied the difference between the microscopic approach and microscopic approach. Okay, in case of macroscopic approach, certain quantity of matter is considered for the analysis. In the case of microscopic approach, the events occurring at molecular level being taken into consideration. Certain quantity of matter is considered in case of macroscopic approach. Okay, and here, according to the microscopic approach, the system composed of a number of the small discrete particles known as the molecules. Here, the events occurring at molecular level being taken into the consideration. And the macroscopic approach is also called as classical thermodynamics. Microscopic approach is also called as statistical thermodynamics. In case of macroscopic approach, the small number of variables are required to know the state of matter or to know the state of system. In case of microscopic approach, the large number of variables are required to describe the state of matter. And the effects can be perceived by human senses in case of macroscopic approach. For example, the pressure, temperature, volume, etc. easily you can perceive by our senses. Okay, suppose if there is a change in temperature in a body, definitely we can sense. Okay. On the other hand, the microscopic approaches, whatever the effects produced by microscopic approach cannot be sensed by human senses because the events occurring at molecular level. Okay, the variables involved in the macroscopic approach are pressure, volume, temperature, etc. And the variables includes, in case of microscopic approach, are kinetic energy, rotational energy, and vibrational energy. And simple mathematical techniques are required for macroscopic approach, and complex mathematical and statistical techniques are required for microscopic approach. Okay, and one more difference is that the variables in case of macroscopic approach can be measured with the measuring instruments, because for temperature we can measure with the help of thermometer, thermocouple, pyrometer, etc. Okay, and here, in case of microscopic approach, the variables like kinetic energy, rotational energy, vibrational energy are very difficult to measure. Okay, these are the differences between microscopic approach and microscopic approach. Okay. Next, we discussed the thermodynamic system. Okay, first you should know the thermodynamic system. It is the quantity of matter or the region in the space upon which our attention is concentrated in the analysis of a problem. That is the definition of a thermodynamic system. Thermodynamic system is divided into the three types. One is the closed system, second one is open system, and third one is isolated system. Okay, closed system is also called as system of fixed mass. Okay, the mass of the system remains constant. Only the energy transfer takes place between the system and surroundings. Remember, thermodynamics mainly deals with the energy transfer. Okay, and also the mass transfer. Closed system, it is a system of fixed mass. Only the energy um, uh, transfer takes place between system and surroundings. Surroundings means whatever the things external to the system, that is called as mm, surroundings. Okay, and system, we are having a boundary. Okay, boundary may be fixed one or it may be movable also. Okay, the boundary is the layer which separate between system and surroundings, and system and surroundings together, we're calling it as universe. In case of closed system, the mass of the system remains constant. Only the energy transfer takes place between system and surroundings. Okay. Example is heating of liquid or fluid or water in a closed container. Okay, so there will be energy transfer takes place between system and surroundings, but the mass of the system remains constant. That is the example. And open system is the one in which both mass transfer and energy transfer takes place between system and surroundings. All the engineering device what we come across, okay, are the examples of open system. For example, gas turbine. Okay, we're having separate chapter called as hydraulic turbines. Okay, all are open system turbines, compressor, air conditioning, refrigeration. So in all the cases, the mass transfer as well as the energy transfer takes place. All the engineering devices are the examples of open system. And third one is the isolated system, is a system in which neither energy nor mass crosses the boundary of the system. Okay, there is no mass transfer, no energy transfer takes place between system and surroundings. We can tell the isolated system is the system of fixed mass and energy. So these are the three main thermodynamic system. Okay, and the example of isolated system is a thermos flask. In case of thermos flask, okay, there is no heat transfer and no mass transfer. Okay, so whenever they ask explain these terms, we have to draw the diagrams. Okay, these are the diagrams, and you have to write the definition with examples. And we studied thermodynamic properties. Okay, every system has thermodynamic certain characteristics by which its physical condition can be described. Okay, so every system has certain characteristics by which its physical condition can be described. For example, volume, temperature, pressure, etc. And these are all macroscopic in nature. Intensive property. Okay, so these are the properties which are independent of mass. Example, pressure and temperature. Extensive properties are the properties which are related to the mass. Okay. Yesterday I was telling density. You remember density is the intensive property. Okay. Density is the ratio of mass by volume. So mass and volume both are the extensive property. So the ratio of extensive to extensive becomes the intensive. Please remember, density is the example of intensive property. But the volume and energy are the examples of extensive property. Okay, density, I'm telling again, it is the example of intensive property because it is the ratio of the extensive property to extensive property. The density is given by mass by volume. So both are the extensive property. The ratio gives the intensive property. Density is example of intensive property. Okay, next we studied thermodynamic process. Okay. Thermodynamic process. When the path of the system is completely specified, then the change of state is called as thermodynamic process. Can you tell what is the difference between adiabatic and polytropic? Anybody? What is the difference between adiabatic process and polytropic process?
Sir, in adiabatic, no heat transfer, and in polytropic, heat transfer is there.
Good. Okay. What is the equation? Do you know? Equation, you know, in case of adiabatic process?
PV to the power gamma is equal to C.
Correct. Good. What about polytropic process?
PV to the power N is equal to constant.
Good. Okay. So we are having mainly five processes in the thermodynamics. One is constant volume process. Second one is constant pressure process. Third one is isothermal process. Fourth one is adiabatic process, and fifth one is the polytropic process. Okay, and I explained all the PV diagrams. Okay, so I'll explain once again. So first one is constant volume process. Okay, constant volume process is also called as isochoric process. Okay, should remember the name also. Another name for constant volume is isochoric process, and it is represented by the vertical straight line because the volume remains constant. Here, now the 1 to 2. So one is called as state point 1, and 2 is state point 2. So thermodynamic process is when the path is completely specified. It is called as thermodynamic process. Okay, here we are going to take the system from state point 1 having its own properties like P1, V1, and T1. When it undergoes the sequence of changes, it reaches final state 2. Okay, and we are having P2, V2, and P2 are the properties at state point 2. Here V1 and V2. V1 equals to V2, hence you have to represent by the vertical straight line. And here it is P1 and it is P2. And this is the x coordinate is V and y coordinate is P. Okay, we have to take like that only. This is the PV diagram. Like that, we are coming across so many HS diagram, TS diagram, and TV diagram. Like that, we are having so many diagrams. But TV diagram is the most important diagram from thermodynamic point of view. Second process is constant pressure process. It is also called as isobaric process. So constant pressure process, the pressure of the system remains same, but only the change in volume and temperature. Here you see the diagram. So here constant pressure process. Okay, the system is process is taken from state point 1. Okay, then it reaches state point 2. So this is the constant pressure process. P1 and P2 are same, and V1 and V2 are different. Okay, this is the representation of constant pressure process on PV diagram. The second process. And third process is called as constant temperature process or isothermal process. Okay, here both pressure and volume changes. Okay, so this is the nature of curve. Okay, this is the nature of curve in case of constant temperature process. And equation is PV equals to constant. How we get PV equals to constant means we are having the ideal gas equation. PV equals to MRT. Okay, P is pressure of the gas, V is volume of the gas, M is mass of the gas, R is general gas constant, and T is temperature of the gas. Okay. M is constant, that is the mass of the gas remains constant. R, general gas constant, that is also constant. And in case of isothermal process, T is also constant. So we can write the equation as PV equals to constant or PV equals to C in case of isothermal process. Here it is a state point 1, it is P1. Then it is a state point 2, it is P2 on y coordinate. Okay, next coordinate it is V1, and here it is V2. So this is the representation of isothermal process. So it is a hyperbola in nature, 1 to 2. Next, we are having the adiabatic process. Okay. Adiabatic process is the one in which there is no heat transfer takes place between system and surroundings. Okay. So we're having certain device where the adiabatic wall is provided to protect the the transfer of the heat from system to surroundings, okay, especially in some devices. So we are having the adiabatic one, for example, in case of boiler and those things. So boiler is a device closed metallic vessel where the steam formation takes place from water at constant pressure, okay. In order to protect the transfer of the heat from the device to the surroundings, the adiabatic wall is provided, okay. Adiabatic process is the process in which there is no heat transfer takes place between system and surroundings, and the nature of curve is same for isothermal, adiabatic and polytropic, but only the change in equation. You remember the nature of curve for isothermal, adiabatic and polytropic, all are same. They are hyperbolic in nature, but only the difference in the equation. In case of isothermal process, we have the equation as PV equals to constant, and in case of adiabatic process, so we are having the equation PV raised to gamma equals to constant, where gamma, it is a Greek word, and it is a ratio of specific heat, that is Cp by Cv. Okay, the Cp is called specific heat at constant pressure, and Cv is specific heat at constant. Cp is specific heat at constant pressure. It is the amount of heat required to raise the unit mass of the substance through unit degree rise in the temperature at constant pressure. That is Cp, and the value of Cp is 1.005 kilojoules per kg Kelvin for air, and Cv is specific heat at constant volume. We can define Cv as the amount of heat required to raise unit mass of the substance through unit degree rise in the temperature at constant volume, and the value of Cv is 0.718 kilojoules per kg. If you take the ratio 1.005 divided by 0.718, you get the value of gamma as 1.4. Remember, the value of gamma is 1.4 for air. Okay? This is the equation, and also the PV diagram. And last process in thermodynamics is called as polytropic process. Polytropic process is the process where the transfer of the heat takes place between system and surroundings or within the system itself. And once again, the nature of curve is hyperbolic in nature, okay, and it follows the law PV raised to n equals to constant, where n is called as polytropic index. In case of adiabatic process, gamma is called as adiabatic index or ratio of specific. But in case of polytropic process, n is called as the polytropic index. Okay, you remember the major difference between adiabatic process and polytropic process is that in case of adiabatic process, no heat transfer takes place, and in case of polytropic process, the heat transfer takes place between system and surroundings. Okay, and which follows the law PV raised to gamma equals to constant. Polytropic process follows the law PV raised to n equals to constant. And gamma is always the ratio of Cp by Cv. On the other hand, the n polytropic index is just a index. Okay, maybe less than 1.4 or maybe greater than 1.4, depending upon the type of gas used in the process. That is the difference between adiabatic process and polytropic process. Okay, you do remember all the nature of curves for 5 processes. And one more is that, okay, we studied thermodynamic process is a process, okay, when the path is completely specified. Okay, as for example, you take here, that is, we are having the initial state and final state, having the initial properties P1, V1 and T1, and here P2, V2 and T2. We are having another process called a cyclic process. Okay. Cyclic process is defined as, it is also called as thermodynamic cycle, is defined as it is a series of state changes such that the final state is identical with the initial state. Now you see the PV diagram here. We are having the initial state point C. Okay, so having the properties P1, V1 and T1, you take any properties and it reaches the final state A by following path B. Okay, undergoes These are the state changes. We are having the intermediate state points. Here C is the initial point and A is called as a final state point. Initially we are having P1, V1 and T1, and finally we are having the properties P2, V2 and T2. Now I'm going to take the process back from state point A to C by following path D. So in that case, here first it undergoes from initial state to final state A and come back to the initial state. So the initial state and final states is identical. Okay. So such kind of process we are calling it as cyclic process. Cyclic process or thermodynamic cycle. But you remember whatever we study, it's not a cyclic process, just it is a thermodynamic process because it is not returning to the initial state. Suppose if it returns from final state to initial state, so such kind of process we are calling it as the thermodynamic cycle. So what we discussed yesterday and today, these are all just the thermodynamic process. Thermodynamic process means the initial and final states are not identical and different. But in case of thermodynamic cycle, the initial and final conditions are same because it undergoes the change of state from initial state to final state and come back to the initial state. Okay? So initial state is identical with the final state. Kind of process is called as the cyclic process. One more thing. Next, we are having these two systems. One is homogeneous system, and second one is heterogeneous system. Homogeneous system is the one which is having a single phase. That is called as homogeneous system. Okay. For example, you take water. Okay, it is in a single phase. So you take the solid ice. Okay, that is in a solid phase. That is homogeneous system. Heterogeneous system means when a system comprises of more than one phase. That is called as heterogeneous system. Can you give the example of heterogeneous system? Anybody? It is a mixture of two phases. Heterogeneous system.
So water and oil.
Water and oil, good example because the oil which floats on the surface of water. Okay, good example. The mixture of water and oil. Can you tell why oil floats on the surface of water? What is the reason?
So because its density is lesser than water.
Good. Okay. Do you know the values of density of water and oil? Approximate values?
So water is 1,000 something.
Good.
Oil, I don't know.
Should be lesser, right? Lesser than 1,000, right?
Yes, sir.
Yeah, good. So the density of oil is less than that of density of water. Hence, the oil floats on the surface of water. You remember the density of water is 1,000 kg per meter cube. We are going to express density in terms of kg per meter cube. So oil usually it varies from 700 to 800 kg per meter cube, depends upon the type of oil. Okay, that's why it floats on the surface of the water. Okay. Once again, suppose you take the water and steam mixture, that is also the example of heterogeneous system, and vapor or steam floats on the surface of the water because the density of steam is far less than that of density of water. Okay, we are going to learn this concept in chapter called as boiler. Okay, so where the steam formation takes place from the water at constant pressure, the steam floats on the surface of the water. Okay, due to the low density of steam as compared to water. And one more, we are having a liquid called as mercury. Okay, mercury is heavier fluid than the water. Okay, the density of mercury is 13,600 kg per meter cube. Remember, 13,600 kg per meter cube. Density of water is 1000 kg per meter cube. Uh, Anybody, do you have any idea about the density of steam, approximate value? Density of steam. Density of steam is far less than that of density of water. It's approximately 1.52 like that. That is the density of steam. These are the systems, homogeneous system and heterogeneous system. Next, coming to the laws of
Excuse me,
thermodynamics.
sir.
Tell me.
Sir, can we consider the Carnot cycle an example for thermodynamic cycle?
Yeah, it is thermodynamic cycle only. Okay, Carnot cycle is a thermodynamic cycle, but it is a theoretical cycle. Okay, we are having so many cycles like you are going to study petrol cycle, diesel cycle, everything in an internal combustion engine. Carnot cycle is a thermodynamic cycle and it is theoretical cycle. In case of Carnot cycle, we are having we achieve the 100% efficiency. Remember, but no heat engine gives the 100% efficiency. Carnot cycle, we are having mainly a four process. Okay, as I said, cycle means it start from initial point, it undergoes sequence of operation and comes back to the original state point. We are having the two isothermal process and two adiabatic process. In case of Carnot cycle, it is a thermodynamic cycle only, but it is not a practical cycle. Okay. Do you have any idea about why it is not used as a practical cycle? Anybody you know? Do you have any idea?
Sir,
Carnot
because
cycle.
of the efficiency.
Good. Efficiency. No, what is the reason? We'll achieve maximum efficiency in case of Carnot cycle, but actually it is not possible.
Yes, sir.
Why means I'm telling you, in case of Carnot cycle, we are having just a minute. Okay, share that slide if it's okay. We are having four process. Okay, two isothermal process means two constant temperature process and two adiabatic process. Okay, in case of Carnot cycle. Okay, so when you start the engine, okay, we cannot change the speed of the engine in between. Okay, but in case of Carnot cycle, it is not possible. So in order to achieve the maximum efficiency, we have to stop the engine in between. It's not possible at all. Once you start the engine, it has to undergo all the four process and then it reaches the final state. It is not possible because isothermal process means constant temperature process to be carried out very slowly to attain the constant temperature. On the other hand, the adiabatic process to be carried out at a faster rate. Okay, but practically not possible. Okay, because two processes in a slow condition and two processes are in a fast condition, it is not possible because we cannot change the speed of the engine in between. Hence, Carnot cycle is practically not possible. So we get the maximum efficiency in case of Carnot cycle, and it is used as a reference cycle for other cycle. Okay, so we are having a chapter. We are having subject called as basic thermodynamics and applied thermodynamics in mechanical engineering. There we are going to learn Carnot cycle. Remember, it is just a theoretical cycle. Practically, it is not possible. Uh, Meantime, we are going to study the petrol cycle and diesel cycle. I'm going to explain all these cycles in internal combustion engine chapter.
Thank you, sir.
Now, zeroth law of thermodynamics. Zeroth law of thermodynamics. Totally, we are having four laws of thermodynamics. One is zeroth law, first law, second law, and third law of thermodynamics. Before that, you should have the idea of temperature. Okay, as I said, temperature is a thermodynamic property. Okay, you can define temperature as the temperature is measure of intensity or degree of hotness in a body. Okay, so temperature is going to measure by various devices like a thermometer. We are having a radiation pyrometer, then we are having a thermocouple, etc. Depending upon the range of temperature. Normally, what we are seeing is thermometer, and sometimes we use thermocouple for higher range of temperature, and also the radiation pyrometer. Radiation pyrometer is mainly used to measure the temperature above 1000 degrees Celsius. Okay, and zeroth law of thermodynamics. If a body, you see, if a body A is in thermal equilibrium with body B, and also separately in thermal equilibrium with the body or system C, then the system B and C are in thermal equilibrium with each other. So this is the statement of zeroth law of thermodynamics. For that purpose, you have to draw the simple diagram. You have to show three bodies: system A, system B, and system C. You have to join A with B, A with C, and also B with C. Okay. In statement, if a body or system A is in thermal equilibrium with body B, and also is in thermal equilibrium with body C separately, then the bodies B and C will be in thermal equilibrium with each other. Okay. So in mechanical engineering, we are having a equilibrium condition. There are three equilibrium condition. One is mechanical equilibrium, second one is thermal equilibrium, and third one is the chemical equilibrium. So one more equilibrium is there, that is called as electrical equilibrium. So we are not going to consider that electrical equilibrium in mechanical engineering. So mainly we deal with three equilibrium condition. One is mechanical equilibrium, second one is thermal equilibrium, and third one is the mechanical equilibrium. Okay. So first one is thermal equilibrium. Thermal equilibrium means the temperature of the body and surrounding should be same. That is called as the body and the surroundings are in the same temperature condition. Okay, that is called as thermal equilibrium. Okay, suppose we don't have some, for example, you consider body A is having around 40 degrees Celsius and surrounding temperature is at 20 degrees Celsius. Then the body interacts with the surroundings, and after some time it attains the same temperature as that of surroundings. Okay, in that case we are calling the body and the surroundings are in thermal equilibrium with each other. Okay, the same concept we are using here, that is body and surroundings have the same temperature. So apart from thermal equilibrium, we are having the mechanical equilibrium. Mechanical equilibrium means it is a balanced force exists between system and surroundings. If there is an unbalanced force, in that case, the body interacts with the surroundings till it reaches the pressure of the surroundings. Means the body and surroundings should have the same pressure. That is called as the mechanical equilibrium. Third one is chemical equilibrium. Chemical equilibrium means there is no chemical reaction takes place within the system. That is the chemical equilibrium. So zeroth law of thermodynamics states that when a body A is in thermal equilibrium with body B and also separately in thermal equilibrium with body C, then the bodies B and C will be in thermal equilibrium with each other. Okay, so this is the statement of zeroth law of thermodynamics. Okay, do remember you have to draw this diagram for giving the statement of zeroth law of thermodynamics. Next, coming to the definition of work and heat. As I said, the thermodynamics mainly involves with the energy transfer. So energy, we are having the different forms of energy: mechanical energy, chemical energy, nuclear energy, vibrational energy, rotational energy, the work energy, heat energy, etc. But from thermodynamics point of view, we are going to discuss mainly two types of the energy. One is work and one is the heat. Already studied the mechanics definition of work or physics definition of the work is it is the product of force and displacement. And unit of work in mechanics is Newton meter. When the force is applied on a body, then it moves in the direction of and it gives the displacement. The product of force and displacement, we are calling it as the amount of work done. Force is going to express in terms of Newton, and displacement we are going to express in terms of Newton, meter. So the unit of work is Newton meter, and 1 Newton meter equals to 1 joule. Okay, so the product of Newton meter is joule. Okay, that is the mechanics definition of work. But in case of thermodynamics, the work we are going to define in a different way. Okay. So for that purpose, you see, this is the diagram, the closed system. Okay. So we are having a pulley, and this is called as a stirrer, and the shaft is connected and known quantity of the fluid is enclosed in the system. Thermometer is fixed to know the temperature at the beginning and at the end, and a weight is attached to the pulley. So just consider thermodynamics system consisting of known quantity of fluid enclosed in a vessel. Okay, and we are having the shaft is the wheel, pulley, and the weight is connected to the pulley. Here it is a stirrer. Okay, so just at the initial point, we are having the thermodynamic properties P1, V1, and T1. Okay. Now, what I'm going to do, just you have to lower the weight. Okay, lower the weight means starting I am having somewhere here. Okay, then as you lower the weight, okay, can you tell what happens? As you move down the weight to a certain distance, what happens? Starting, I'm having the weight here, having the initial thermodynamic properties P1, V1, and T1. As you move the down, okay, as you rotate the pulley, then the weight will move down to a certain distance, say dx. Okay, so what happens as the pulley rotates, then the stirrer also rotates. Okay, stirrer also rotates. So as the stirrer rotates, the work is done on the system. Because of this stirring work, there will be a change in thermodynamic properties takes place. Initially, we are having P1, V1, and T1. So after stirring work, so that we get the thermodynamic properties as P2, V2, and T2. Okay. So how the rising or lifting of the weight takes place. Okay, so work is done by a system on the surroundings. Here you see the work is done. So it is done by a system on the surroundings. How if the sole effect on everything external to the system could have been rising of a or lifting of a weight. Means starting, just you consider this as a system. Okay, so when the stirring work takes place, in that case there will be a change in thermodynamic properties takes place. Because of this change in the thermodynamic properties, which is external to the system, means there'll be whatever the change in thermodynamic properties takes place inside the system, it affects the surrounding also. So because of the change in thermodynamic properties in the surroundings helps to lift the weight by certain distance. Okay, that is the thermodynamics definition of work. So how we are going to define means the work is said to be done by a system on its surroundings if the sole effect means the net effect on everything external to the system would have been the rising or lifting of a weight. Okay. So this is the thermodynamics definition of work. Once again, Here we are having the force applied, and displacement is just moving of the weight from initial position to the final position. That is nothing but your displacement. It is similar to your mechanics definition of work, but we are going to define in terms of thermodynamic properties. So this is the thermodynamics definition of the work. Okay. So work is said to be done by a system on the things external to the system, which helps to rise or lift a weight. That is the thermodynamics definition of work. Okay. You have to write the thermodynamics definition of work. Okay. Next, so we are having the sign convention. You remember how we are going to represent. Okay. Work is done by the system is positive, and the work is done on the system is negative. You see this diagram, the work is done by the system is positive, and the work done on the system is negative. The sign convention for the work. Okay. So we are having two definition of work. One is mechanics definition of the work, and second one is the thermodynamics definition of work. And unit is same. Okay, there is Newton meter only, there is joule only, but the definitions are different. Okay, so mechanics definition of the work is the product of force and displacement, and the thermodynamics definition of work is, okay, I'll explain once again how we will get this one is, let us consider a closed system, okay, consisting of a known quantity of fluid enclosed in a vessel. Okay, so the thermometer is inserted to measure the temperature at beginning and at the end, means initial and final state, and stirrer is fixed inside the system, which is connected to a pulley and wheel arrangement. A weight is connected at the bottom of the wheel. Okay. Starting, we are having P1, V1, and T1. So as you start the pulley, the stirrer work takes place. So stirrer work results in the change in thermodynamic properties. Okay, and which helps, means it affects the things external to the system in surroundings. So as there will be a change in thermodynamic properties in the surroundings, so which helps to lift the weight by certain distance. That is nothing but dx, the thermodynamics definition of work. And the notation is the work done on the system is positive, and the work is done on the system is negative. Next, we are having one more term called as heat. Okay, the heat is a form of energy. Okay, heat is a form of energy. How it takes place? It takes place by virtue of temperature difference. Okay, heat is a form of energy which takes place by means of virtue of temperature difference only, and the heat always flow from the higher temperature gradient to lower temperature gradient. That concept I am going to explain in second of thermodynamics. Okay, heat is also form of energy which occurs by means of virtue of temperature difference, and the unit is the joule. Okay. And regarding sign convention, you see, okay, whenever you add the heat to the system, that is the energy is increased, means Q is positive. Whenever the heat added to the system is positive, whenever the heat taken from the system is negative. Suppose if you withdraw some quantity of heat from the system, in that case the energy of the system decreases. Hence it is represented as negative. Okay, but it is different for work done. If work is done on the system, it is negative. If work done by the system is positive. If the heat is taken into the system, it is positive. When the heat is taken out of the system, it is negative. So these are the sign convention. Okay. And the unit is same, that is Newton meter. Okay. And we are having three modes of heat transfer. One is thermal conduction, and one is thermal radiation, and third one is thermal convection. Remember, there are three forms of energy, uh, heat energy. One is thermal conduction. Okay. Second one is convection, and third one is radiation. Conduction. So I think you might have observed, okay, as you heat some metallic rod, so the temperature gradually increases, okay, and then the temperature flow from higher temperature gradient to lower temperature gradient, okay. So that is an example of the thermal conduction, okay, within a solid body, okay, or when the two bodies are in direct contact, and the heat transfer takes place from one body to another body. That is an example of conduction. So the thermal conduction is a mode of heat transfer which takes place in a solid body or between the two different bodies which are in direct contact with each other. Okay, that is the mode of heat transfer. That is conduction. Okay, I think you studied conducting materials and those things. So copper, brass, next silver, gold. These are all very good conductors of heat. These are the conducting materials. Conduction is the mode of heat transfer, so which takes place in a body itself, or when the two bodies are in direct contact, then the flow of heat takes place from one body to another body. That is an example of thermal conduction. Second one is thermal convection. Convection is a mode of heat transfer which takes place between a body and the medium. For example, when you heat the water in an open vessel, okay, in that case, the heat transfer takes place from the surface of the water to the surface. The mode of heat transfer called as convection. Another example is the hot air uh, flowing over the buildings. Okay, that is also example of convection. And radiation is. Do you know what do you mean by radiation?
Heat transfer without a medium.
Correct. The heat transfer without a medium. For example, whatever the rays we are getting from the sun is the best example of radiation, okay, through electromagnetic waves. Okay, the medium is not required, so the transfer of heat from one body to another body without affecting the medium or without requiring the medium. So these are the three modes of heat transfer. Can anyone give the example of conduction, convection, and radiation taking a common example? So means you take one example which should involve all the three processes like conduction, convection, and radiation. I gave the separate example like that. You think of yourself and tell me, okay, the common process in which all the three modes of heat transfer takes place, like conduction, convection, and radiation. Anybody? Can you think of?
Excuse me, sir.
Tell me.
I have a situation. I don't know if it's correct or wrong,
Tell
but
me.
if we take a Bunsen burner and heat
Hmm.
water in a tin can, first it will be radiation because of the flame, which heats up the tin
Good.
can, and then heat
Hmm.
will be transferred to the water, which is through conduction,
Good.
and then the
Good.
water rises up to the top because of convection.
Yeah, good example. Okay, it's correct. Okay, whatever think of, no, it's correct. Like that, you should think of yourself. Okay, so as I said, thermodynamics plays very important role. Okay, so it involves physics, chemistry, mathematics, plus your general thinking, analysis, everything. So whatever you give the best example, good. Okay, like that you have to think of. Next, similarities between the heat. Okay, I defined heat. Okay, heat is mode of, it's a form of energy which occurs by means of temperature difference. Heat added to the system is positive, and heat is taken from the system is negative. Okay, sometimes they may ask, explain the similarity between work and heat transfer. Okay, so whenever it comes to the similarities, both are energy interactions. Okay, both are transient phenomena, both are boundary phenomena. Means it crosses the boundary. Okay, and they are not the property of the system, and both are back functions. Okay, these are similarities. Coming to the dissimilarities. Okay, you see, the heat transfer takes place by virtue of temperature difference only, no parameter involved in the heat transfer. But the work is not like that. Okay, so the work transfer takes place by means of the change in any property, like the change in pressure, change in volume, okay, change in magnetic field, okay, change in potential, okay, like that. Whatever the parameters, we are having so many parameters in work, but heat is not like that. Heat transfer always takes place by means of virtue of temperature difference only, but the work transfer or the work energy takes place by means of the difference in other parameters also. Okay. And second one is, we can tell the heat is a low grade energy and the work is a high grade energy. We can completely convert the work energy into heat energy, but the reverse is not possible. We cannot convert 100% the heat energy into the work energy, because the heat is low grade energy, and so many losses takes place. Because of this one, heat cannot flow from lower temperature gradient to higher temperature gradient. So we can tell the heat is a low grade energy and the work is a high grade energy. As I said, the complete conversion of the heat into work is not possible, but the complete conversion of work energy into the heat energy is possible. Okay. As I said, the heat occurs mainly by virtue of temperature difference. We can tell it as heat is a thermal energy transfer related to the temperature, but the work is mechanical energy transfer across the system boundary. It occurs by virtue of difference in different parameters. And you remember, there are only the three modes of heat transfer, as I explained: conduction, convection, and radiation. Only three modes. Apart from this one, there are no modes of heat transfer at all. But coming to the work energy, we are having many kinds of work energy, like displacement work. We are having shaft work, electrical work, flow work, stirrer work, and magnetic work. You see, so many kinds of the work are possible, but only there are three modes of the heat transfer: conduction, convection, and radiation. So these are the dissimilarities between work and heat transfer. Okay, so concentrate on definition, mechanics definition of work. Next, thermodynamics definition of work, because you have to explain that thermodynamics definition of work with a simple example, what I explained. Next, we studied that sign convention for work transfer and heat transfer, and then definition of the heat, unit of heat, sign convention of heat, different modes of heat transfer, then dissimilarities, similarities between work and heat transfer. Okay, so you have to think of yourself and you have to write these points. Work is a low grade, a high grade energy. Heat transfer is low grade energy. Complete conversion of work is possible. Complete conversion of heat is not possible. So only there are three modes of heat transfer. There are many number of the work transfer. Okay, like that you have to think. I hope you understood all the concepts. Any doubts, students? Any doubts? Any doubts in today's class? Like work transfer, heat transfer. Good. Okay. Now, all of you, please enter your name in the chat box. Everyone have to enter your name in the chat box for attendance purpose. Everybody? Okay. Everyone enter. 37, 38 students are there. Everybody, please enter your revision. Once I stop the recording, so that your name will not be recorded, hence you please enter as early as possible. 37 students are there. Okay, all of you have to enter in the chat box. Okay. All 37 students. I'm seeing only few names. Okay, all 37 are not there. Please enter all your names in the chat box. Okay, guys, hope you all of you entered your name in the chat box. I'll stop the recording now and I'll stop the session now.